Okay, Algebra 2, Lesson 1. We're going to talk about successive differences and polynomials. This is your first flipped lesson, and just a little bit of what I talked about when we discussed it in class. It's really important that you watch the lesson somewhat slowly and utilize the pause button and the rewind button, not always the fast forward button. We discussed being a passive learner versus being an active learner. A passive learner, an example would be if you just, sit down at your kitchen table with your feet on the table, just watching the lesson as it goes by, versus an active learner where you're actively taking place in your education and you've got, a pencil in hand with your classwork in front of you and you're taking notes and you utilize the pause button and the rewind button and the play again button. Reviewing things that didn't really make sense, making notes on your paper. If you don't understand something, to ask me when you get to class tomorrow. So you really have to slowly watch the lesson and make sure that you engage in what's going on. There'll be quite a few instances where I will ask you to work on something on your own, and that's when you're going to have to pause the lesson and work on it, and then push play and see what happens. Just don't watch me do the problem. You learn much, much more if you do the problem on your own and then watch how the solution took place, how I did it. So let's go ahead and get started. Okay, first thing we're going to do is try to look at the patterns we have here. So we're going to look at the relationships between each row and the row above it and the row below it. To start out, you see here I have a row of sequential numbers, then the next row. Okay, do you see any patterns that took place here? Pretty simple. Then we have this row and the row after that. Okay, this 3 is written between the 1 and the 4 on purpose. How did we get there? The 5, how did we get there? Then 7, etc. And then how do we get to the 2? Okay, we're doing math operations here. How do we get to the 2? What you see is true, okay? To get here, it's hard to see. But here, how do I get from 2 to 4? And then just notice the pattern, 3 to 9. So this first row, I just see numbers. Okay, the second row, I've got square. Okay, I go from 1 to 1 is squared. 2 to 4. 2 squared is 4, etc. Now, how do I get from the 3? Okay, 4 minus 1 is 3. 9 minus 4 is 5. 16 minus 9 is 7, etc. So those are called my first differences because I subtracted the first time. Now, 5 minus 3 is 2, 7 minus 5 is 2, 9 minus 7 is 2. Since I subtracted a second time, these are called my second differences. So we notice the patterns in the numbers above. We notice the relationship between each row and the row above it and how to label the rows based upon the relationship. We can do the same thing with a little bit more difficult numbers. Okay, if you get out your calculator, or if you're really awesome at math with decimals, which some of you are, you can notice 2.4 squared, 3.4 squared. So this first row are just my numbers. The second row is the square. Then, if I subtract, I've got my first differences. And if I subtract again, I have my second differences. Awesome. So, assuming the pattern we have here, we explained all the patterns. We are done with this one. Okay, so let's look at an example. The first example in your classwork is, what is the sequence of first differences for the linear polynomial given by ax plus b, where a and b are constant coefficients? I'm going to set up a really simple table for us to start through this one. Okay, I'm going to have x and the polynomial, the linear polynomial, means it makes a line. Okay, where I'm going to have x is, excuse me, 0, 1, 2, 3, and 4. I'm going to try to make it not look like my little kids wrote this. So if we plug in 0 for our linear polynomial, we would get 0 for x, just plain old b, 1 for x, a plus b, 2 for x, 2a plus b, 3 for x, 4 for x. All right, now let's look at our differences. Remember, we subtract that way. So we have a plus b minus b, and that gives us a. Okay, subtract up. 2a plus b minus a plus b. Notice parentheses means we distribute our negative. We get 2a minus a is a, b minus b is 0. 3a plus b, minus 2a plus b. Distribute that negative again, and we get a. And again, you guys probably figured all this out by now. So my sequence is going to be bracket, I got a, I got a, I got a, dot, dot, dot. It's going to be a forever. So the first differences sequence is right here. Okay? For first degree polynomials, the first differences are constant. Giving you time to write this too. And equal to a. Makes sense. The next question says, what is the sequence of second differences? Well, if we take this and subtract, 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 you get a minus a, a minus a minus a. We have a pattern. Nice bracket, 0, 0, 0, dot, dot, dot. So the second differences are a sequence equal to 0. Awesome. Let's move on. So I have 3 more examples. I'd love you to push pause and work through at least one of them just to make sure you know what's going on, and then you can move on. I'm going to push pause and work through the problem. So go ahead and push pause now, work through one of them, and then push play, and you'll see how it goes. So if you see, I just finished this first one. There is my work. Go ahead and push pause and check it out. Check out the numbers, make sure they make sense. I'm going to work on one more, and then we'll move on. Okay, there you go. Go ahead and push pause and check that work out. Our sequence is, that was terrible. That's funny, sorry. Three, 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 dot, 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 close brackets. Okay, example 2. Find the first, second, and third differences of the polynomial given by filling in the blanks in the following table. Okay, I think you know enough to work on this one by yourself. So if you could please push pause, I'm going to work the problem also, and then we'll talk through the answer. So go ahead and push pause. All right, if you see here, I took where x equals 1, subtracted it from x equals 0, got our first differences, okay? Took where x equals 2, subtracted it from x equals 1, x equals 3 minus x equals 2, etc. Okay, that was my first differences. Then I found my second differences, taking this equation, subtracting it from this one. So 3a minus a is 2a, b minus b is 0. 5a minus 3a is 2a, b minus b is 0. Okay, etc. So we have our second differences. Then subtracting again, 2a minus 2a is 0. Okay, we'll always see when we have a second degree polynomial, our second differences are going to be constant, our third differences are always going to be 0. It's a pretty cool pattern. Okay, second differences are a constant, 2a. This is our second degree polynomial. Okay, our second differences are 2a. So what we're learning here is the second differences for a polynomial like this, it's going to be a constant value of 2a. The second differences hold for any sequence of values where any sequence of values of x, where the values in the sequence differ by 1, just like the opening exercise we did. So here we have a second degree polynomial, and our second differences are constant, and they're 2a. Okay, so what's our conjecture? Do you guys even know what a conjecture is? I've always thought of a conjecture as a guess. Okay, it's a guess. So what are you guessing that your pattern is going to be? I'd actually like to talk about what your conjecture is for a third degree polynomial. Okay, we've done some first degree polynomials, some second degree polynomials. What's your conjecture of a third degree polynomial? Okay, let's think about it. So, your third degree polynomial, your first differences aren't going to be constant. Your second differences aren't going to be constant. You're really looking for what your third differences are going to be. So if you go back, okay, now for a third degree polynomial, we're trying to guess. What do you think the third differences are going to be? Okay, sort of an open-ended question. Some of you may think that your third differences will have a constant value of 3a, which is not correct. Okay, so we're going to work through another example to try to figure out what the third differences are going to be on our own. Here you go. Go ahead and push pause and work through it. Okay, you have your classwork in front of you. So our third differences of a third degree polynomial all have the constant value 6a. If a different sequence of values for x that differed by 1 was used instead, so a different sequence of x that only differed by 1, so we have, these are all differing by 1, the third differences would still have the value of 6a. Okay, that's our constant. Pretty interesting. So, what do you think what's your conjecture about the fourth differences of a sequence generated by a fourth? So what are our fourth differences by a fourth degree polynomial? What do you think it is? Okay, think about it. Okay, we went from 2a to 6a. So what do you think it's going to be for your fourth degree? I'm pausing on purpose. Okay, you might think that, let me see if I have another page here. We're probably going to have to go back to some pre-algebra or something here to explain this. But if we have a second degree polynomial, we got 2a, and that really is 1 times 2a, which is 2a. Okay, a third degree polynomial, 1 times 2 times 3a, which is 6a. A fourth degree polynomial is 1 times 2 times 3 times 4a, which is 12, 6 times 4, 24a. If we had a fifth degree, can you figure out the pattern what to do? It's actually a times n factorial. Remember, factorial means if it's like 5 factorial, it's really 1 times 2 times 3 times 4 times 5. That's what factorial means. Okay, a little bit of a crazy question. Another conjecture. Could you try to figure out what is the n plus 1, like the n plus 1 difference of a n degree polynomial? For example, what is the fifth difference of a fourth degree polynomial? Okay, think about that for a second. If you go back a lesson or two, or a slide or two, I'm sorry, and you looked at, say, the third difference of a third degree polynomial, your constant was 6a. Or the second difference of a second degree polynomial, your constant was 2a. The fourth difference of a third degree polynomial, your constant was 0. So the fifth difference of a fourth degree polynomial, your constant is going to be 0. So your n plus 1 difference of this difference of that polynomial will always be a constant of 0. Okay, last example, I believe. Yep. So what type of relationship does the set of ordered pairs xy satisfy? How do you know? This is what we're sort of getting into. So we're going to fill in the blanks in the table below to help us decide what degree polynomial is this? So we can look at this as a bunch of data. Does this data satisfy a quadratic relationship, a cubic relationship, a linear relationship, etc.? So there are ways for you to discover what relationship data has by using these differences, which is really, really interesting. So we're going to look at our differences. So let's go ahead and do this math. I'm going to push pause so you don't have to watch me subtract. So since the third differences are constant, the pairs represent a cubic relationship. So here we see, since the third differences are constant, the pairs represent a cubic relationship. So we're going to grab some of this data and try to find out what the equation is. We're going to grab some information here. So our xy pair, oh so sorry, that will happen a lot. I'm going to grab these two ordered pairs and use them. When x equals 0, y equals 2, which if we put into standard form, y equals a x cubed plus b x squared plus c x plus d. All of this stuff cancels, and we have d equals 2. Let's just check that ordered pair, 3 and 20. So I'm checking the 323. So now we have to do the hard work. Okay, find the equation of the cubic form, that's just standard form, that all ordered pairs x, y satisfy. Give evidence that your equation is correct. So we're going to have to page back and forth a little bit. Something we know for a cubic relationship is 6a, which is our constant for a cubic relationship, is always going to equal 6. Solve for a. You have a is equal to 1. So if you page back, so I grabbed the ordered pair 1, 1 and the ordered pair 2, 6. I'm going to plug them in just to a standard cubic equation. So xy, y equals a, which is 1. Sorry, handwriting. So y equals a x to the third power plus b x to the second power plus c x plus, let me page over here again. Cool. Okay, next, xy. Y equals a x cubed plus b x squared plus c x plus 2. All right, I'm going to simplify these. I'm going to write my first equation first again. 1 equals, we're doing some basic algebra here, 1 plus b plus c plus 2. The next equation simplified is 6 equals 2 cubed, 8, plus 4 squared, 2 squared is 4, plus 2c plus 2. Okay, simplify these a little bit. I'm going to get all the numbers to one side. Let's see. 1 plus 2 is 3. 1 minus 3 is negative 2. What's left over? B plus c. Okay, 8 plus 2 is 10. 6 minus 10 is negative 4. 4b plus 2c. I need to solve the systems of equations, which you learned at the end of Algebra 1, but we can relearn it. I'm going to go ahead and multiply this top equation by 2. That gives me negative 4 equals 2b plus 2c. Make sure I'm doing this the way yep. And I'm just going to subtract the second equation from it. So -4 minus -4 cancels. 2 minus 4, -2. 2 minus 2 is the b's, or the c's canceled out. Divide by -2, divide by -2, b equals 0. Awesome. Okay, I'm going to plug that back into another equation. I'm going to take that, just plug it into a earlier equation. -4 equals, since b is 0, oh, positive 2c, so sorry. So I just grabbed that and plugged it in to this equation. I made b 0. Divide both sides by 2. C equals -2. And now we have our final equation. This is what the goal is, and it took a long time, didn't it? Y equals A is 1. B is 0, so I don't need to write it. So ax cubed plus bx squared, b is 0, plus c, which is -2, x to the first power plus d. This is our final answer. Note, it says give evidence that your equation is correct. I'm going to do that right up here. I'm going to check one of the other ordered pairs. Oh, for goodness sakes. In the equation that I made. XY, so 23 equals x cubed, so 3 cubed minus 2 times 3, that looks awesome, plus 2. Okay, this is cubed. So we have 3 cubed is 27 minus 6 plus 2. 27 minus 6 is 21, plus 2 is, in fact, 23. I apologize, that does look like my small children wrote that. Okay, that was a rough final example, wasn't it? All right, in closing, what are some of the key ideas that you learned today? Okay, I would say sequences whose second differences are constant are a quadratic relationship, which is squared. And then we have third differences are constant. Okay, that gives us a cubic relationship. All right, last but not least, like I talked about in the syllabus, I reserve the right to give you an entry ticket to get into class tomorrow that you have to answer really quick before you can start your classwork. And we'll see how that goes. Nice work today.